So the first number I'm going to start with is number 2, and it's just to make sure that that you don't find the instructions for it confusing or anything like that. But it's something I would assume you'd be able to do. Number 2 says piece of k is equal to this statement, this expression. And based on that, we want to find piece of k plus 1. And this is just a necessary skill for the second part of induction. It's nothing crazy. Right? In the second part of induction, I assume this thing. I assume that this statement is true for piece of k, some statement about positive integer. And then I want to be able to make the substitution of k plus 1 in there. So that's all this is asking you to do. It's not too crazy. So for this one, we just need to make the substitution of k plus 1 in there. So this is 4 over, I put a k plus 1 in here for k. Right? Instead of k, this is k plus 1. So it's k plus 1 plus 2. So that's k plus 3. K plus 1 in here for k. K plus 1 plus 3 would be k plus 4. And that's it. Right? That's all I need to be able to do. That's all that's asking me to do is to make that substitution. Now, in induction, we would go on to prove this statement, but for these first few problems, it's not necessary. Let's see, for number 5, it's just a little bit different looking statement. Piece of k is equal to 7 plus 13 plus 19 plus ... plus 6 times k minus 1 plus 1 plus 6k plus 1. Alright, so we just need to make a substitution correctly. A piece of k, make this p a little bigger, so sub k plus 1. Well, these parts don't have anything to do with k, so they just stay the same. 7 plus 13 plus 19 plus ... plus, and here's where we start making our substitution. Alright, so instead of k, we're going to substitute in k plus 1. So we have 6 times k plus 1 minus 1. K plus 1 minus 1 would just be k. 6 times k, and then there's a plus 1 there. Plus 6 times, okay, so here's a k. I'm going to make the substitution of k plus 1 instead of k, and then plus 1. To finish it up, just, I'd rewrite this again, and then this would be 6k plus 1 plus, well, and then we got to distribute the 6 through here. We get 6k plus 6 plus 1. This is 6k plus 1 plus 6k plus 7. That would make this a 12k plus 8, or you might stop right here, since a lot of times when they have a rule broken up the way that they do, it's because it's useful to look at it that way, right? It makes it simpler to look at. So, if they have it written like this, you might want to keep it in those parentheses, but I mean, this would be correct as well. So that's it. Those are those first few problems. That's all that's talking about. All right. Now let's try number 7, an actual induction process here. It says prove what they're saying using induction. So they're saying 2 plus 4 plus 6 plus 8 plus... So what we're doing here is adding up a bunch of numbers, and this is what we're going to do with induction a lot in this section, is prove that there's some formula for adding up certain kinds of numbers. So what kinds of numbers are these? 2, 4, 6, 8. So these are the even numbers, right? This is 2 times 1, 2 times 2, 2 times 3, 2 times 4. 2 times n would be the even integer. Of course, that's given in this problem. They say 2n is the formula for finding the nth term. All right, that's the nth term, but the nth sum, which adding up the first n even numbers, they're saying it's just n times n plus 1. Yeah, that's what they're proposing. And rather than, looking at a bunch of examples and trying to draw pictures or whatever, we're going to use induction to prove it beyond the shadow of a doubt. Okay? So, the first part of induction. Show that it works for the first case. The first case is the first even number. The sum of the first even number is just 2 plus nothing else. So 2. S sub 1 is equal to 2. Now we want to see, does this formula, if I use this formula for S sub 1, does it work? So does S sub 1 equal this formula? I'm not sure, but we're going to try and see. So I'm going to put a 1 in here. 1 times 1 plus 1. 1 plus 1 is 2 times 1. That's 2. So yeah, it does work out, right? That question is answered. The first case works. So the first part of induction is proven. Second part of induction. 2 parts to the second part. Assume that to find the sum of the first k even numbers, assume that I can use the formula. Right? I'm done. I'm done assuming things. The next thing that I need to do is, with that assumption, I'm going to show that the next number, or the next sum, I should say equals, I should prove that the next sum also can be found using the formula. K plus 1 times k plus 2. I'm just taking k plus 1, so here instead of k I have k plus 1. Instead of k I have k plus 1 plus 1, that'd be k plus 2. So I want to show, verify, that this formula can be used to find the sum of the first k plus 1 even numbers. All right? So what we're trying to show is that 2 plus 4 plus 6 plus 8 plus all the way up till 2k plus 2 times k plus 1, that you add all these up instead of having to add them all up, I could just use this formula. I want to prove that that's true. To prove that, remember that we have assumed that we can use the formula for this part of the sum. This is going to happen a lot in induction. You're going to write down the sequence, you're going to rewrite all these terms using the assumed formula, and then see if you can add this on and get it all to look like this formula. That's pretty much how induction goes at this level. So you add up the first k even numbers, and we assume that k times k plus 1 is going to work. And then we're going to add on 2 times k plus 1 and see if we can get this expression to look like this guy right here. So, like I said, you can work your way through here. You can kind of work from both ends. You know, I could say, well, this, if I FOIL this out, this is k squared plus 3k plus 2. Okay, and if I can do something with these guys and make it look like that, then I know that I've got a proof by induction. So let's distribute the k. That's k squared plus k plus distribute the 2k plus 2. This is k squared, combined like terms, plus 3k plus 2. There it is. And I know that since I FOILed this, that this can be factored to get this formula, which is what I was trying to find in the first place. So QED, we've proven it. By induction, we can use this formula to find the sum of the first however many integers, or however many even numbers that we want. Okay? Let's try another. Number 11. 1 plus 2 plus 2 squared plus 2 to the third plus, I'd like you to just take a second. I'm about to write the formula to find the nth term in this sequence. And just as practice, pause the video and see if you can figure out what I'm about to write here. Okay? So these are, here's a sub 0, a sub 1. This is a sub 0, not, so that should be a sub 0, a sub 2, a sub 3. I'm sorry, this should be a sub 1, a sub 2. That's how we like to start. A sub 3, a sub 4. Okay. And I see, oh, the base is 2 for all these. I think this is probably a 2. And it's raised to a power every time. I'm thinking it's not n, because this is 4 and this is 3. This is 3, this is 2, 2, and then a power of 1, and so on. So it must be not n, but n, 1 less than n minus 1. Okay, so and that is the formula that they say to use. They say 2 to the n minus 1. And it verify that it works here as well. It's going to be 2 to the 0, and that's 1. All right, so they're saying to add up all of these guys. Let me make sure I'm writing this down correctly. 2 to the n minus 1. Now be careful. These look similar, but they are different, right? This is 2 to the power of n minus 1. This is 2 to the power of n, and then just subtract 1 from this number, okay? So be careful not to confuse those two. They're saying if you want to find the sum of the first n powers of 2, right? This is 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4, and so on. And you want to find the first n powers of 2 and add them all up, then you can use this formula. Okay, so part 1 of induction would be to show that it works for the first case. So here's the first case. Let's add up all of these numbers here. Well, 1 plus nothing else is just 1. So s sub 1, the sum of the first 1 power of 2 is 1. Let's see if this formula works. Does it work? I'm going to put a 1 in there. 2 to the 1 minus 1. That's 2 minus 1, that's 1. So it works. That's the first part of induction. We've done it. Okay? And part 2 then. First part of part 2 is assume. That's the easy part. We're going to assume what? That to find the sum of the first k powers of 2, that I can use this formula. So it'd be 2 to the k, and then subtract 1. Then I want to show that for the next term, if I want to add on the next term, I could also use this formula. 2 to the k plus 1 minus 1. Alright, so let's get to work. What we're trying to show is that I can add up all these powers of 2. 1 plus 2 to the first plus 2 squared plus 2 to the third plus dot 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 plus 2 to the k plus 2 to the k plus 1, right? Here's how I find or 2 to the k minus 1. That's what it should have been. The formula is to take the term that you're on, subtract 1. So if this is k minus 1, then this would just be k, just by itself. Okay. So here we go. This looks an awful lot like that, and it should. So we're adding up these first few terms, and we're assuming that we can use the formula to do this. And the formula is 2 to the k and subtract 1. There's the formula, and we're also then going to add on 2 to the k. Alright. Remember, we're trying to prove this. 2 to the k plus 1 minus 1 is going to be this sum we're looking for. So, let's see if we can do that. I see this minus 1, and I see this minus 1, and I'm thinking, there's the minus 1 part of it. So let's put these two guys together. 2 to the k plus 2 to the k minus 1. Now, if only this were equal to 2 to the k plus 1, I would be in good shape. Well, think of these as like terms. This is 2 to the k plus 2 to the k. Just as a side example in red, if I had x plus x, what would that be? It'd be 2x. If I had y squared plus y squared, what would that be? That's 2y squared. If I had, tennis ball plus tennis ball, that would be 2 tennis ball. Right? Whatever I'm adding 2 of, it's the same as saying, well, just 2 times that thing. Right? So 2 times 2 to the k minus 1. Well, now I have a 2 times a 2 to the k. I have the same basis here. This is 2 to the 1. This is 2 to the k. What do I do with the exponents when I'm multiplying? I add the exponents. 2 to the k plus 1 minus 1. And that was exactly the formula I was trying to show works. It does work. So by mathematical induction, I've proven it. All right? So we'll continue more in the next video.